The mechanism for oxymercuration demercuration is complicated and involved, and it's not something that you would need to be able to draw from memory per se. But it's important to understand conceptually what each of these different reagents are doing. First, so that you can see a connection between this and other reagents. That makes it easier to remember these things. Otherwise, they're long lists of unrelated facts. It's hard to keep track of them all, whereas if you understand conceptually what each of these things are doing, you'll see that out of hundreds of reactions, there are only a few small number of things that are happening. You'll see a unity behind them that will make these more memorable. And also, as you go on in chemistry, it will be the concepts of how these reactions work that come back, say, in biochemistry. So if you just approach this as a memory exercise and memorize these specific molecules, then you'll have to start all over again in biochemistry. But if you understand the concepts of how things are working, you'll see patterns, and when you get to biochemistry, all the concepts will be exactly the same. You'll just see them applied in a new way, and so it'll be almost as if you already know everything in the class. You're just seeing it applied in a new context. Also, these reactions are reactions that you'll want to know for at least this semester and for all of organic chemistry too. They come back, they never go away. And if you just memorize them as letters and numbers, then you will forget them quickly because they weren't meaningful in the first place. So I don't want to go through the complete mechanism here, but I want to go through enough of the mechanism so that it will be easier to remember the recipes here. It'll be easier to think about what each of these things is doing, and so it'll both help make it easier for you to remember this recipe, and it'll make new recipes that you see in the future more understandable. For example, this NABH4 is going to come back a lot in organic chemistry too, and if you understand what it's doing now, then your life in the future will be that much easier. Okay, so again, this is not going to be the complete mechanism, this is just an overview, a conceptual overview of sort of the general steps that are happening here. So, in our mechanisms for hydrohalogenation and acid-catalyzed hydration, we saw that pi bond, those pi electrons, is the nucleophile on that carbon chain. Okay. Now here's a big principle that will come back. If you look at this first thing, the very first element we see is Hg. Hg is mercury. Actually comes from the Latin words hydro argurum. Hydro is water, and argurum is referring to silver. For example, Argentina is the land of silver, supposedly. That was what the name came from. And so, water silver, or quicksilver, is an old English way of referring to it. It was the name for mercury because mercury is the only metal that's a liquid at room temperature. So that's where the A and the G are coming from. You have the H in hydro and the G from silver. So it's mercury. Now, one big trend you're going to see throughout organic chemistry is metals, the role of metals. Metals have really low electronegativity, and so they often act as electrophiles. They give their electrons away. So in this case, it's being bonded to two things. Now you'll notice at the bottom of this recipe there's a 2, and so you're going to be bonded to this OAC twice. So we know we're going to have an oxygen. Let's talk about what the AC is. AC is an acetyl group. Now that is 2 carbons long and has a double bond to an oxygen on one of the carbons. Okay, that specific structure is not the most important thing in the world. What is important to recognize is that mercury is a metal. Metals have very low electronegativity, and so that's going to be slightly positive. The oxygens, of course, would be slightly negative. Now, these electrons in these bonds are repelling each other. Mercury has very low electronegativity, so it's hard for it to hold on to those electrons. So one of these pushes on the other one. It takes its electrons, leaves the molecule. This mercuric acetate, which is a white solid. So when you put that into solution, these vibrate around, one of them pushes off, and now you have this mercury not with a partial positive charge, but this mercury with an acetate on it, not with a partial positive charge, but with a full positive charge. So that's your awesome electrophile. And your pi bond nucleophile can come in and attack that. Okay. Now when it attacks, your analysis would probably be really similar to what you would think would happen in a hydrohalogenation reaction. You're trying to think, which carbon would the mercury go on? There are 2 carbons involved in the double bond. Where does the mercury go? Well, if the mercury attaches on the less substituted carbon, then you would form a carbocation on the more substituted carbon, and that would be more stable. And this is where it's useful to know the mechanism, because it gives you information about these notes here. Oxymercuration demercuration adds an H and an OH, and it does it in a Markovnikov way. That's the same as acid-catalyzed hydration. Acid-catalyzed hydration is really cheap, really safe, and so why would you ever do oxymercuration demercuration, which involves mercury, which is expensive and bad for the environment and toxic? You would do it because the one advantage is that you don't get carbocation rearrangements. Well, why not? This is one of those ways that you can see knowing the mechanism will help you remember that. Otherwise, it's going to be very hard to associate that with this recipe. If you know the mechanism, or at least if you conceptually have a grasp of it, you would see that this mercury has this lone pair here. And that lone pair is attracted to the positive charge. So whereas this carbocation could rearrange in acid-catalyzed hydration, in oxymercuration demercuration, the mercury attacks it and forms this sort of ring. This sort of ring. Now the mercury does have a positive charge here, and it leans a little bit more toward the less substituted carbon, because it bounces around like these bonds are like little springs. They're constantly moving around, and so nothing is even, but as it bounces around, this carbon here can handle a slight positive charge better than this one, so the mercury leans toward the less substituted one, and on the average, the more substituted one has a slight positive charge. So it's because the lone pair on this mercury is stabilizing the carbocation that you don't get rearrangement in this oxymercuration demercuration. This is called a mercurinium ion. Just a mercury, and then the ium often is just a suffix given to ion, so a mercurinium ion. Well, we've done our sort of oxymercuration, or rather we've done our mercuration. We've added mercury onto the molecule. Now we need to add some sort of oxygen, and that's what the water is here for in the second step. Now in this case we're using water, but in the future we're going to use water as a nucleophile, but in the future you could use any other different nucleophile. For example, you could use a hydroxyl group that has a carbon on one side instead of a hydrogen, like water. So this is another unity that you'll see, another thing that will help you in the future, knowing that this water here is acting as a nucleophile, and so you can replace it with other nucleophiles. And when you see that, a similar recipe, but with the water replaced in the future, knowing this mechanism will give you a grasp of what's going to happen there. Well, let's say you have water. How does the nucleophile attack? The water is slightly negative, and the oxygen here is going to attack the slightly positive, more substituted carbon. And so now you can see why this is going to be Markovnikov addition. The OH goes on to the more substituted carbon, not the H. Now that breaks that sort of triangle bond to the mercury, and you have this. And now you can understand the name, the first part of the name. We've added oxygen and we've added mercury, oxymercuration. Now all we have to do is to take the mercury off. In other words, now all we have to do is demercuration. And so the overall process is oxymercuration, demercuration. Now at first there's just a step with it where another water molecule does a proton transfer to help stabilize this positive charge. Remember, proton transfers change stability. So if you take an H plus away, then you can stabilize a positive charge. These electrons go back there. And so you get something like this. Oops. Okay, so far we've explained the name. You add oxygen and mercury, so oxymercuration, and then we're going to take the mercury off, so demercuration. We've shown how you get this OH here. We've shown the role of mercury in stabilizing the carbocation intermediate so that it does not rearrange. And we've shown that whatever the second thing is here, we used water, that's going to act as a nucleophile, so that determines what adds here. Imagine, though, it could be H2S, and then you'd have SH there instead. So there are multiple possibilities here for that. Now we need to explain this NaBH4, and the name for that is sodium borohydride. Oops. So sodium borohydride. Okay. Well, what you'll notice there, just like in mercury, so you see this coming back already, is that you have a metal. Boron is a metal. It's the top metal in group 3A. It's just to the left of carbon on the periodic table, just above aluminum. So it's a metal. Metals have very low electronegativity. Now, if you see there, it's NaBH4, sodium borohydride. So the boron is bonded to 4 hydrogens. Boron has very low electronegativity, so it loses electrons to the hydrogens. Usually you think of very electronegative elements as being slightly negative. Oxygen, nitrogen, chlorine, bromine. Hydrogen is not very electronegative. It's all the way at the left of the periodic table. And yet, if you pair it with a metal, then you can turn the hydrogen into a nucleophile. It's a really powerful concept. You can take an element that has just moderate average electronegativity, and you can turn it into a nucleophile by bonding it to a metal. Think of all the reactions you can do with that. If you have a hydrogen nucleophile, think about how that could affect substitution reactions. You can replace a leaving group with a hydrogen by using something like this. So that's sodium borohydride, and that's borohydride, I should say. Hydride, by the way, we've seen a hydride shift. Hydride is when you have a hydrogen with 2 electrons. So we've seen those in carbocation rearrangements where a hydrogen will take its 2 electrons and sort of move over toward a carbocation to help it rearrange. It's called a hydride shift because you're dealing with a hydrogen and 2 electrons. Here, one of these hydrogens is going to get pushed off of this molecule. The bromine is a metal, so not very electronegative. All of these bonds are pushing against each other, repelling each other. So one of them is going to kick, the 3 of them are going to kick one of them off. That hydrogen with its electrons, hydride, is going to act as the nucleophile. So that's why we have sodium borohydride. Now that whole thing has a negative charge, and sodium is there as a counter ion to help stabilize that so it doesn't explode or react with the first thing it comes across. So sodium borohydride. Ultimately, and this is sort of a simplification here, but our purpose here is to understand the concept to help us remember this reaction and to see connections in the future. It's not necessarily to understand every nut and bolt in this thing. Ultimately, what's going to happen here is one of these hydrogens is going to act as a nucleophile. It'll take its electrons, attack this carbon, and kick the mercury off. Now that's not exactly what happens, but it's sort of conceptually what happens. And that's how you get your demercuration. So you have OH on the more substituted carbon and the H on the less substituted carbon. That H is the one from sodium borohydride. And then you have the mercury compound still floating around in the solution. But you ultimately, in the story of the carbon, is that you turned the double bond into you added an H and an OH onto it, and you did it in a Markovnikov way that did not allow rearrangements to happen because the mercurinium ion stabilized the carbocation. Okay, so hopefully now this weird mixture of letters and numbers has some meaning to you. It will be easier to remember. Hopefully now it's a story with characters that have particular personalities, reactivities, and that explain these details in a way that's more memorable than just trying to memorize random letters.